माझं एक सजेशन होतं, तिथे स्टुडिओ डिपार्टमेंट आहे ना, त्याचा उल्लेख करा. आभार.
अच्छा, आपण ग्रे विजन म्हणतो त्याच्या
ते पण आणि हौसलला विचार प्रॉपर नावाचा
सारंग आणि
ते देतात, कारण ग्रे विजनला आपण पैसे देतो.
घेऊ नाव लिहून घेऊ Okay. Start. Hello. Yeah. Okay. Good afternoon, everyone. It's a great pleasure for me to welcome all of you in this Science Club colloquium that we have been organizing for the last almost 2 years, wherein we invite experts from various fields to our campus to enlighten us about topics, hot topics for centuries, hot subjects. And in the last this semester we had two other speakers. The first one was Professor K.S. Waldia from the geology background, where he spoke to us about the restlessness in Himalayas, various activities going on in Himalayas and how it is affecting the environment. After that, we had Professor Ravindra K. Kohli, an ecologist, who talked about aliens, pathogens that are coming and affecting the flora and fauna of various regions. And today we have with us, I can say, our very own Professor Rajaram Nityananda, who was director at the NCRA from 2000 to 2010, to enlighten us about thermodynamics, a topic which is very close to physics as well as chemistry and including biology. So I would like to introduce Professor Rajaram Nityananda. Is a physicist who works on solid-state physics, liquid crystals, optics, image processing, and gravitational dynamics. He currently works as a professor at the Azim Premji University, Bengaluru. He was formerly the director of the National Center for Radio Astrophysics and also TIFR, and the Center for Interdisciplinary Sciences in Hyderabad. He also serves as an associate editor of the Journal of Astrophysics and Astronomy, published by the Indian Academy of Sciences, and also the chief editor for Resonance, the journal for science education, published by Indian Academy of Sciences. He is also the chairman of the board of directors of the National Institute of Technology, Tiruchirappalli, and Chennai Mathematical Institute. Professor Rajaram entered the Material Science Division, National Aeronautical Laboratory, in 1969 to work for his PhD degree. He joined Raman Research Institute as a member of the scientific staff in 1975 and became professor in the year 1995 and served as dean during 94-96. In the year 2000, as I said, he moved to Pune to serve as the center director, NCRA TIFR, a position which he held till February 2010. He also served as a council member for the Indian Academy of Sciences during 1989-91 and was a visiting professor at the Department of Physics, Indian Institute of Science, Bangalore from 89 to 95. He has been the editor of Pramana, the Journal of Physics, and Journal of Astrophysics and Astronomy, and served on the editorial board of Resonance and Current Science. He was a member of the International Steering Committee of the Australia Telescope National Facility. Professor Nityananda is a fellow of Indian National Science Academy, fellow of the National Academy of Sciences, and also the Indian Academy of Sciences. He is also the recipient of the Karaimanikan Srinivasa Krishnan Memorial Lecture Award from INSA in 2004. I welcome him and request him to talk on thermodynamics still hot after 3 centuries. Professor Nityananda, please. Thank you.
Thank you, Professor Kumbar and the University Science Club for giving me this chance to come back to a place where my family and I spent many happy years in this beautiful campus. And part of the happiness was the opportunity to interact with colleagues in the Pune University and this department in particular. So I've been in this hall quite a few times. Some of the lectures have even been on the blackboard, but since I couldn't use the blackboard, I did the next best thing to make my view graphs white on black. Okay. Now, thermodynamics is taught in undergraduate and postgraduate courses. My guess is it's not very popular, right? It's also slightly mysterious because you undergo a course on mechanics where things are very clear cut. You know, particles move, they obey some definite laws, they collide with each other, and you can say what happens after the collision, so on and so forth, or orbit. The moment you come to thermodynamics, you stop looking at individual particles, right? You have some very large Avogadro's number of particles. So some completely different concepts take over. Temperature, of course, we have some intuitive idea what it is, right? Heat again, and perhaps the most mysterious is this quantity called entropy, which you get by dividing Q divided by T. Okay, so this was anyway my experience when I learned thermodynamics. And the other interesting thing was, at some point, you start studying heat engines, right? Even if it is a physics course or a chemistry course, you have to learn. You know, you take a gas, compress it, and so on. Take in some heat, give out some heat at a lower temperature. So it's an intriguing subject. Then you go to postgraduate, so you think things will become clearer, but actually that's not what happens. Now people say, all right, so now we will understand things in terms of individual atoms and molecules, but they introduce a lot of terms like macrostates, microstates, ensembles, partition functions, and then you have to be very good in calculus. You have to take a function of many variables and differentiate it, okay? So that's what I call technology. And in all this, perhaps the beauty of the subject and the conceptual aspects get pushed aside, okay? And the aim of this talk is to try and, you know, give you a feel for that. So it will actually be like the typical tour operator who takes you to Panchgani and shows you 20 points quickly and brings you back. And if you are interested in any of those points, you should go back and spend more time there, okay? So let us begin at the same place where the subject began, with this very brilliant contribution by Carnot, French engineer actually. See, people were building steam engines and so on, but they didn't really understand what was happening. And he seems to have given a very deep analysis. It is so deep that we use the same analysis even today, that he somehow identified the importance of this quantity. People knew the importance of heat transferred and also temperature, but he realized that taking the heat transferred and dividing it by the temperature gives you something new in the sense. So I have called it like karma. So the heat engine absorbs some heat at a higher temperature, all right? So you have Q by T, whatever it is. Carnot did not tell you what it was. And then you have to get rid of the same Q by T or more at a lower temperature. To make the engine efficient, you should waste as little heat as possible at a lower temperature. So he identified the importance of this quantity. You can create it. If you run the engine badly, then you may generate more heat than what is necessary in the exhaust. Most of our buses do that. But you can transfer it, right? So the meaning of this, or at least part of the meaning of this, was brought out a little later. So we are talking of early 19th century for Carnot and middle 19th century for Clausius. So the scene now shifts to Germany. And he realized that actually you don't have to think only of heat engines. You can think of any object which is taken through some cycle, and in that process it absorbs heat, it does some work, all right? At each point in the cycle you keep track. How much heat did it take from the surroundings and what's the temperature at which it took. So no longer are you confined to just a heat engine. It could be anything, okay? And then he, using similar arguments to Carnot, they are very clever arguments actually, which are there in the textbooks. he identified the importance of this quantity. Okay. Now, the important distinction I would like to make is that this is actually a property of a given state of the system. You have prepared the system, you may have prepared it in many different ways, but the energy, for example, is something which we all accept is a property of that state. You don't worry about how it got the energy. Just as if you have so much money in your bank, you don't worry whether the money came in by NEFT or by check or by draft or by cash. These are all different mechanisms for transfer. So similarly, work, heat and all are different mechanisms for transferring energy to a body. But this particular property, if you reach this state by reversibly transferring heat, this property he realized how important it was. He gave it a name, entropy. I have given you the spelling in German. He still didn't tell you what his meaning was, but it really, after energy, it was the new quantity to enter the consciousness of physicists, and it was terribly important because he could prove the second law of thermodynamics, which we all are familiar with, that in a closed system, this quantity can either remain constant if you are very, very careful, but if you do anything rash, anything quickly, anything irreversible, this quantity will only increase. This was the second law of thermodynamics, and it seemed to have a very wide validity. It explained a lot of the common observations that heat will flow from a hotter body to a colder body, but not in the reverse direction. If I have a gas in which, let us say, the number of molecules on one side is greater than the number of molecules on the other side, then the numbers will equalize by either the movement of the molecules or diffusion, and then you never see it coming back. Now, should we be surprised? Based on our common experience, no. Irreversible things are happening to all of us all the time. I mean, certainly human beings, we age, we never grow younger, right? However, if you think of it fundamentally from the laws governing atoms and so on, it is a bit surprising because those laws are supposed to be reversible. Okay? And for example, a planet could go around the sun in the opposite direction. If two billiard balls collide and take off, you can send them back and they will reverse. So this was something which worried people. But the laws of thermodynamics, as formulated by Clausius, explained a wide range of phenomena. So what was missing in the middle of the 19th century was an understanding of what this quantity is. Everyone knew it's very useful. So now I have put here two great figures who helped us to clarify the meaning of entropy. So on the left you have Boltzmann, okay, and he gave, first of all, he gave a mathematical formula for a system. S is the entropy, log, I'll tell you what W is, and you have to take the logarithm to get S, and you multiply it by K. So this K is actually needed because, as defined by Clausius, entropy has some units: heat divided by temperature, energy divided by temperature. But if you just take the logarithm of W, it won't have any units. So you need a conversion, right? So Boltzmann called it K, and everyone else calls it Boltzmann's constant, and they put a suffix with a B, which is what we will do. Now W is this very interesting thing. He says, look, here is air in this room. All right. Do you know what every molecule in the room is doing? No. But you know the total energy, you know the total volume, and so on. So you have very, very limited knowledge of what's going on in the system, but you make a virtue of that. You say, all right, so there are many, many states of the system which are all consistent with whatever knowledge we have, and that is W. And he says, if you take the logarithm of W, that is entropy. Now, of course, you can always make a definition. Now, the greatness of Boltzmann was, he showed that at least for gases, he gave a very detailed theory of gases, how things collide and so on, and he showed that this agrees with the Clausius definition. So here are two things which look completely different. So one person tells you to keep on adding heat in small quantities and divide by temperature and add it up. The other person says, imagine all the possible states of the system, W, which, not all the possible states, but those which are consistent with what you know, the volume, the energy, and so on. It's something of a miracle that these two should agree, but they agree. He also gave a mathematical proof based on collisions that what he defined as W for a gas will increase with time. Okay. So, I have just put a little explanation of why he chose the symbol W. It is not for ways, number of ways, but it is for this German word. German is a very compact language. So, what is expressed in a long sentence in English is one word in German, which is in quotes, and it means probability. So, the idea is that systems attain the most probable state. Okay. So, very simple example would be if you toss a coin 100 times, much more probable that you get 50 heads and 50 tails than you get all 100 heads. I should qualify this statement. When I say it is more probable to get 50 heads, 50 tails, I am not telling you which are the heads and which are the tails. If I told you the first 50 should be heads and the next 50 should be tails, that is as improbable as getting 100 heads. But the moment you say it is all mixed up, then the number of ways of doing it is much more, and basically this is what was constructed by Boltzmann, but specifically for gases. And this task was taken up by, in fact, probably the first great American theoretical physicist, Gibbs. So, first of all, he has two major contributions, one purely in thermodynamics and one along the lines of Boltzmann for understanding thermodynamics from the point of view of molecules and their interactions. Okay. So, it was mentioned in the introduction that thermodynamics is important for chemists, but the form that chemists use was created by Gibbs, because Boltzmann confined himself to a gas which has only one species, but a real chemist would be mixing many different things. They would be combining in different ways. They might form different phases, solid, liquid, and so on. Those phases would have boundaries. So, he wrote this. Gibbs also did not publish much. So, I do not think he would have got much funding or many awards in the current climate. In fact, his essential publications are two. A long book called, 130-page paper called Equilibrium of Heterogeneous Substances, which has all that I told you. Okay. And then on statistical mechanics, which is understanding thermodynamics from the point of view of probability, that is what statistical mechanics is about. He wrote a book and it was published just after he passed away. Okay. It is called Elementary Principles in Statistical Mechanics. Now, he took the idea of Boltzmann, but carried it much further, because he was interested in systems which could be more complicated than what Boltzmann was talking about. So, therefore, he took as general a dynamical system as possible. So, in the case of Boltzmann, these were molecules which are far apart and they would collide. Here they could be, but that way you will never form a liquid. You need attractive forces, molecules need to stick together. So, he formulated a very general theory based on just the general principles of mechanics. And for that he had to introduce various notions. The interesting notion he introduced, which is what I would like to talk about, is called an ensemble. Now, what is an ensemble is somewhat like what I told you in Boltzmann's case. It is not just the state of the system as it is now. It is the state of the system as it is or as it could be based on your limited measurements. Okay. So, I found this word interesting, and while preparing for this talk I looked it up. So, in common language, ensemble is a group of separate things which contribute to a coordinated whole. In fashion it is used. So, if you read page 3 of various things, they will tell you that such and such a film star came with an ensemble of clothes designed by some Ritu Beri or something like that. A group of musicians is called an ensemble. But according to Gibbs, ensemble is a collection of states which the system could be consistent with what you know. You fix the number of particles, and number of particles was an important variable for Gibbs, because he would have particles of different kinds which could react and produce other particles. But this is a very strange definition of, but we use it even to this day, and that tells you why this concept of entropy is so fascinating, because it is not just a property of this system, it is a property of a whole collection of systems of which this is a member. Okay? So, you can think about the philosophical implications of that. Nevertheless, we think we can measure it. Okay? Now, we normally think of Einstein in 1905, clarifying the nature of Brownian motion, nature of photoelectric effect, nature of relativity, all within 6 months. okay, essentially creating all of modern physics, right? But it's also interesting to ask, what was Einstein doing between the age of 20 and 26, since he obviously had such a powerful mind. He wrote a couple of papers on statistical mechanics, okay? And when the Einstein centenary was celebrated in 1979, I had studied a little bit of German. At that time, there was no translation available. I read them. The remarkable thing is that what Gibbs did in 30 years, Einstein did in about 3 or 4 years, without knowing the work of Gibbs, because the work of Gibbs was not published, okay? But he did something, I mean, all his contributions have a flash of insight. So his insight was, take Boltzmann's formula, S is equal to log W, but rewrite it, saying W is exponential of S divided by Boltzmann's constant, right? Now you may say, does it need Einstein to say that if X is log Y, then Y is exponential of X? But the idea is now the following, okay? That let us say you know how to calculate entropy for a system in the present. So let us take the system that we will talk about briefly will be the simplest possible system, a gas where you have more molecules on one side and less molecules on the other side. So you could calculate the entropy of the system, and you could also calculate the entropy when the gas fills the container uniformly, which is more, okay? So does it mean that the container will remain uniform forever? Now Boltzmann already gave you a clue that W is really probability. So what Einstein is telling you in these early papers is that what we call the equilibrium state, the state where the entropy has become maximum, the gas is filling the container uniformly, is the state of highest probability, but there are states of lower probability. So if you measure very carefully the density in 2 halves of the container, it will keep fluctuating. It will, because it's not an impossible state where the density on the 2 sides are not equal. It's just less probable. So Einstein actually gave a theory of fluctuations based on this idea. So that's why I call it fluctuations 1, because we will also see a fluctuations 2 and a fluctuations 3 to the major theme in the 20th century. This was connected to his interest in Brownian motion. So just to remind you, Brownian motion is when you have this very small particle in a liquid, but it's big enough to be seen under a microscope. And this particle seems to be dancing around perpetually, okay? It was a big puzzle until Einstein himself came along and said, this is the motion of this particle. It seems to be extracting energy from the surroundings, start moving, but then again it gives the energy back because it's damped. So one of the very nice ideas he introduced is that there must be a relationship between this damping and the random kicks which is getting from the surroundings, okay? So if it kept on increasing in velocity, that would violate law of conservation of energy. So what happens is the particle keeps picking up energy from the surroundings and giving it back in the form of damping. So one of the byproducts of Einstein's work was a relationship between the temperature and these random movement of the particles, which you call diffusion, on the one hand, and damping, which is if I try to move the particle with some velocity, how much force there is. So that is what he did. So it seems to violate second law because it's actually absorbing heat from the surroundings, converting it to energy. But it doesn't really, because after Einstein, second law is not it's not a law which is enforced 100%, a bit like the law on helmets wearing scooters in Pune or in Bangalore, right? You get punished, of course, if you don't do it, but so every now and then any system will fluctuate away from the equilibrium state, okay? And you can even calculate that based on this very nice formula. So I would like to say that in some sense these effects are a little difficult to observe, but what is happening nowadays is that people are building smaller and smaller electronic circuits and other devices, and these fluctuations have now suddenly become important. So we'll see that as we go along. Now meanwhile, this concept of irreversibility still continued to worry people. They said, okay, look at Newton's laws, it's reversible. And then Boltzmann's own teacher, a famous person called Lord Schmidt, himself questioned his student, saying, you start with collisions which are reversible, and then you do some magic, and then you have produced a second law of thermodynamics which is irreversible, right? And Boltzmann was not able to fully answer these objections. In fact, later in his life, he was very upset that by many things. The sad news is that he actually committed suicide, maybe not only because of thermodynamics, but in any case. And this was really clarified by this couple who lived in Holland sometime in 1930s. They were asked to write an encyclopedia article on thermodynamics. So they sat down and tried to look at all the fundamentals of thermodynamics. The names are, Ehrenfest is the surname, and Paul Ehrenfest is the Dutchman, and she is from Russia. Interestingly, in Russia, a woman could not study science, so that's why she came out into Europe to study mathematics and so on, and they wrote this article together. So they solved this problem of irreversibility once for all, okay? And what was their solution? So their solution was the following. So look at this graph. I think even this cursor is visible, right, which is moving around. So maybe I won't use the pointer. Entropy is plotted on the vertical axis, but it's plotted downwards. So the state of maximum entropy is here, the equilibrium state, and this is just time, okay? So if entropy is very abstract, think of this as the density difference between two halves of a small container. So that density, and then this would be zero density difference, and this would be more and more inequality in density between the two sides, okay? So most of the time it's equal, but every now and then the density becomes different because molecules can move randomly from one side to the other. And Boltzmann's model of a gas, the molecules are more or less independent, except when they collide, right? So you have these fluctuations. Every now and then you may get a large fluctuation. By accident, a larger number of molecules may sit on one side. We'll take an actual example presently. So this curve is completely reversible, okay? So they say that underlying dynamics is completely reversible. Then why is it that we observe the second law of thermodynamics? That's because you went and prepared the system in this state, okay? Now it's interesting that if you prepare a system in a state with very low entropy, most likely it will be somewhere near a peak. Now why is that? Because of course there could be states which are going even more negative, but those are even rarer, because according to this Einstein's formula, the moment you want to go to lower and lower entropy, the fluctuations become rarer and rarer, okay? So that's why you have lots of small fluctuations, very rare large fluctuations. So once you prepare a system, most likely you will prepare it somewhere here, or if you want more density difference, you will prepare it here. And now it doesn't matter whether you run the curve this way or this way, it will go back to equilibrium. So the reversibility problem was solved, but this was really a verbal explanation. But today we know it's the correct explanation, because by 1960s computers were powerful enough to take hundreds or thousands of molecules, put them in a box, evolve them according to Newton's laws. So no cheating, no bringing in heat or anything like that. But sure enough, they could plot this curve and it was completely reversible at the same time. So this paradox was removed, and since people worry so much about reversibility, let me show you a simple example. It looks complicated, but actually it's not. So since Avogadro's number is too large for this slide, I have chosen only 4 molecules, okay? So these are the different possible states of the system. If you are only keeping track of, is the molecule on the left side of the container or the right side of the container? So this is a state in which all the molecules are on the left. This is a state in which all the molecules are on the right. Now molecules are randomly crossing from one side to the other. So from this state, what possible states can you get? So in this case, molecule by the way, these are distinguishable molecules in this case. So molecule number 4 has moved to the right. The remaining 3 are still on the left, okay? So that's one possibility. So we are looking at other states which can come from this state. So here number 3 has moved, here number 2 has moved, and here number 1 has moved. So this state is connected to these 4 states. Now of course, the next thing which could happen is this molecule could move back, but it has many more options now. You have 3 left molecules and 1 right molecule. So any of these 3 left could also move to the right. So see what's happening here. This L, okay, this L has become an R, right? The second L has become an R. So I won't explain every arrow in this diagram, but that is how they were constructed. So now you can see from this you have 3 possibilities, right? Any of these 3 L's could become an R. So this one, and this one, yeah? Each one of these has given birth to 3 possibilities. So 4 into 3 is 12, but you only have 6 here. The reason is 2 of them can give rise to the same possibility. So I just want you to keep in mind the way the arrows are going in this diagram. So you have 1 state here, 4 states here, 6 states here, again 4 here, and again 1 here. So now let us assume that there is no bias in the system. System can move along these, so it's reversible. System can move this way or back. Where will the system spend most of the time? So from here, 1/4 of the time the system will go back, which is a case of decreasing the entropy. But 3/4 of the time it will go here, right, to one of these states. So basically, this is the rule of the majority, because the majority of states have this property of being equally distributed between the two halves. Now, in this case, the majority is not very strong, right? 6 by 16 is only 37.5%. But if you calculate it with Avogadro number of molecules, you will find that states with where the difference is say less than 0.001% will still be the vast majority. So that's the whole point. So this is just an explanation of, so you should never worry about the fact that mechanics is reversible, but thermodynamics is irreversible. Thermodynamics appears to be irreversible because the system basically has no bias, but it spends more time in those regions where you have a very large number of states. One of the units in which physics is measured is Nobel Prizes. Okay, so here are 2 Nobel Prize winners in the 20th century. So now we are in the 20th century, right? Einstein, of course, won a Nobel Prize, but not for his work on thermodynamics, not even for his work on relativity, because Nobel Committee was still a bit scared. They thought something may go wrong with relativity, so they gave it to him for something else. Okay. So, so this is Onsager, one of the great physicists of the 20th century. Okay. He took Einstein's fluctuation theory and he generalized it. So, Einstein's fluctuation theory was, say, for a Brownian particle. So, you had diffusion, which means the particles on the average will move from higher concentration to lower concentration. That is D. Okay. Then you have kT, which is the amount of thermal energy, and then you have this mu. This mu is really related to the resistance which the particle encounters. I told you that there has to be a balance between the random forces which act on the particle and the resistance. So, okay. Now, what Onsager did, he found that many problems you have more than one quantity which you have to keep track of. So, in a metal, for example, you can either heat one end and cool the other end, which is, by the way, quite an important process in energy studies. It's called thermoelectric generation, or you could apply a voltage, and these processes are actually coupled. Okay. So, you can drive electrons by means of heat, you can also drive them by means of voltage, and what is interesting is you might have a temperature difference, but it will produce a voltage, or you might have a current flowing and it might produce heat. So, this is the phenomenon of thermoelectricity, which, as I said, is practically quite important. So, Onsager was able to give relationships of this kind, okay, and he gave it in 1933, and after about 50 years the Nobel Committee woke up and said, okay, this is very important. So, apparently they called up his house. He was already quite old by then. So, his wife picked up the phone and they said, okay, your husband has won a Nobel Prize. So, her only reaction was, is it for physics or chemistry? Actually, it was for chemistry, because in chemistry you do have many of these processes, coupled processes, for which these Onsager relations are very important. The other person who got a Nobel Prize in this area of irreversible thermodynamics, you could say, is Prigogine, later than Onsager, I think. He belongs to, in fact, he created something called Brussels School. So, Brussels is the capital of Belgium, which is a small country sandwiched between Holland and France, and they have a big, like Sri Lanka, they have big disputes between the people who speak French and the people who speak Flemish. But he took up systems near equilibrium first, and then he went to interesting systems, and we will have more to say about these, where apparently you seem to be violating the second law in a different way. One way to apparently violate second law is look at small systems, and occasionally they will go to states of lower entropy. But he said, if I have not a small system but a driven system, so it's no longer isolated. So, classic example is taking a very viscous fluid, putting it in a tray, a metal tray, and heating it from below. So, that is convection. I think we all study about heat transfer by convection, and we take it for granted. that the hot liquid will have a lower density, so it will float up to the top, the cold liquid will sink down, then that will become hot, and there is some kind of cycle. But so this is not, it is really far from equilibrium, because this system is in contact with hot, see, so source of heat at the bottom and it is cooler on the top. Okay. And he found there is a range of systems which form some kind of order. So when you form convection, the convection cells are not random, they arrange themselves in a beautiful hexagonal pattern, which is why Prigogine did not invent that. Bénard is the person who observed it, and it is a beautiful demonstration. You can look it up on the net or maybe even set it up. He also found that there are chemical reactions where normally you would, what are we used to? You mix everything in the test tube, concentration of the reactants and products can keep changing with time, but is usually uniform in space. But in these reactions, you may find variations in space, or you may find the concentration oscillating. So these are all very interesting phenomena, and they remind you of phenomena in biology, which seem to occur in systems which it looks as if order is emerging from disorder, okay, which of course goes against the spirit of second law. Second law tells you that you start with order and you go to disorder. All of you know that, right? I mean, if you stay in a hostel room or in your own house, if you do not put away your books and so on, then you go from order to disorder. But you can also go from disorder to order. So at least for the students, if your parents are going to visit you, some external force, then order will come back. So it looks as if many natural systems follow this kind of paradigm. See, the very fact that you have a hot body and a cold body available to you itself means the system is not in equilibrium. But instead of heat simply flowing from the hot body to the cold body, it actually creates very interesting patterns. And the speculation at that time was that many of the patterns which we see in nature could actually be produced. So now when you look around you, you look at trees or you look at human beings, they are not in equilibrium, right? I mean, if you took a human being and put him in a closed container and asked what is the equilibrium state, all the chemicals would be mixed, right? And they would form some kind of liquid, your 2/3 water. Now why are we not like that? We are not like that because we keep eating food, and right? And of course, it's not enough to keep eating food. You also have to, sweat it out. You have to do some exercise so that, you get rid of the waste products. So this idea, Prigogine was one of the major people, is order emerging because the system is being driven. Okay. Sorry. Now, National Center for Radio Astrophysics and Ayuka and all were mentioned. So I have to bring in a little bit of astronomy here. Okay. Now, gravitating systems are in some ways an exception to some of the things I have told you. Any textbook of thermodynamics will tell you that energy is an intensive quantity. If I have the energy of 1 ml of water, if I take it 2 ml, then it's double, and so on. So these are intensive quantities. And even entropy and so on depends on the total mass. Now, gravitating systems are an exception. Many of you may have seen this formula for the potential energy of two masses, M1, M2, separated by a distance R12. Right. So even if I have a single mass, I can divide it into two masses, m by 2, m by 2. So the potential energy will depend on m squared. Okay. So not proportional to m. Now this makes a very huge difference. The other thing is it's a long range force. So even if I double the distance between two atoms, the force between them may go to 0. Okay. But if I double the distance between two gravitating objects, the energy only goes to half. So for these two reasons, the long range force and because it's proportional to the square of the mass, a gravitating system behaves differently. So sometime early 19th century, I should have had a picture of this gentleman. He's called Jeans. He's an English physicist and astrophysicist. He just, as a thought experiment, he said, let me take a large box of gas so that gravity also becomes important. What will be its equilibrium state? And he found that if I make the box sufficiently large, the uniform state will be unstable. So, however, this actually agrees with the second law of thermodynamics, and I will tell you why. I told you that if I move some molecules from one side to the other side, the entropy goes down. That is true, all right. This happens in a sound wave, for example, right? You compress one region, you rarefy the other region, and that is why it comes back. However, in the case of a very large box, the compressed region would now have a negative contribution to its energy, right? Because you're bringing the masses closer to each other, so it also gets hotter, and that increases the entropy. So for a large enough system, it will prefer not to stay uniform, but it could start forming clumps. Now this is exactly what we believe happened in the early universe, okay? Now G's mathematics had a flaw which was modified. Okay, this capital G small r should be capital G capital R, general relativity. So, so general relativity shows that if the universe starts expanding, even if it is uniform to start with, it will be unstable. Any small amount of mass in one region will acquire more mass, and the entropy will still continue to increase, because as this mass collapses, it becomes hotter. Then of course it may radiate energy, and then the entropy increases still more, because the radiation is now gone and filled a much larger volume, okay? So it's interesting that if you study cosmology, which is a major subject of interest both in NCRA and IUCAA, you can think of gravity as driving all these instabilities, which you make gas into galaxies, galaxies into stars, or the leftover gas around the star into planets, right? But the strange thing is, the system goes more and more out of equilibrium, right? Because the density is not uniform, the temperature is not uniform. So this fundamental law that entropy increases is still valid, but the way it operates on a cosmological scale is to create an interesting universe, rather than a very dull universe in which everything is uniform, temperature is uniform, right? So we should be grateful for that. Now this question used to worry people like Boltzmann. Before this understanding took place, 19th century, people said universe will be headed to a state of heat death. Everything will become uniform, okay? So now we understand that the universe is out of equilibrium and becoming more and more out of equilibrium. Have we answered that old question? And the answer is no. We have only moved the problem to the initial state, the Big Bang, okay? You give me the Big Bang with uniform temperature, nearly uniform temperature, nearly uniform density, then a theorist can make galaxies and so on, but that initial state itself has to be understood, and people are trying to understand it. So this is just to tell you that many of the themes in this talk are actually the subject of open research. Okay, so let me come back, go tune back to the 19th century. On the one hand, Boltzmann of course gave this impressive proof, which also exists, agreed with experiment, that entropy would increase, and one way it would increase is to make the gas fill the container uniformly. The other way is that the molecules get distributed in energy also. Now of course they cannot go on spreading in energy, because energy is conserved. So if one molecule gains energy, the other molecule loses it. So the energy is spread out around the average, according to a law which was derived by Maxwell, okay? Now Maxwell introduced this concept of Maxwell demon. He didn't call it a demon, it's a thought experiment. The thought experiment is same, you have a gas container divided into two, and there is a partition, and there is a gate, a bit like the gate which separates NCRA and IUCAA from. So the person there can decide whom to admit and whom not to admit, okay? So what Maxwell said is, if this being, which others later on people called it a demon, looks at the molecules and says, okay, a hot molecule is coming from the left, let it through. A cold molecule with lower velocity is coming from the right, let it through. Then gradually, number of molecules will remain the same on both sides, but the temperature on the right side will rise, the temperature on the left side will go down, and you will be violating the second law, not in a small system, in a macroscopic system, okay? So this was a real worry. Maxwell himself doesn't appear to have given any answer to this question, okay? And this is a young picture of Maxwell before he stopped shaving, okay? You see the other pictures, he has an impressive beard and all that. Now whenever you have a demon, you need an exorcist to come and tell you why the demon is not really there, okay? And in this case, this is this person who is not so well known. He is a Hungarian physicist of the middle 20th century called Szilard. He later on became somewhat famous, or you could say notorious, as one of the designers of the hydrogen bomb, along with other Hungarians like Teller and so on. But he came up with this very interesting idea. He said, okay, so now go to this figure here. So this is a heat engine, just like the one that Carnot invented, except Szilard took it to the extreme limit. He says there is only one molecule. Okay, it has a hot wall, it has a piston. So how is this engine going to function? So initially, let us say the piston was here near this dotted line. The molecule goes, hits the hot wall, picks up energy, then hits the piston. When it hits the piston, it does some work. It gives up some energy to the piston. Piston in turn may be driving your motorcycle. Of course, with one molecule, you will not get much power in your motorcycle, but whatever. You will get some useful work. It will go back, hit this, pick up energy and go on pushing this. So this is the first step of the Carnot engine, what is called isothermal expansion. Right? The molecule remains at it keeps getting its temperature from the hot wall and it pushes the piston. The next step in the Carnot engine is give up the heat here so that you can push the molecule back. See, if you straight away push the molecule back, you will lose all the energy which you gained by being pushed. So unless you cool down the molecule, you will not be able to push it back. But Szilard's idea was, because I have only one molecule, let me do something different. I will get my energy out, I will not dump some heat into a sink, I will wait. When I learn that the molecule is on the left side, I will quickly move the piston here, I do not have to do any work because the molecule does not collide with the piston. So I am now back, the cycle is now complete. Okay? Again, I can allow it to expand, get some work. So this is the heat engine which has a source, it has no sink, 100% efficient. So can this really work? And this would be against the principles of the second law of thermodynamics. So Szilard analyzed this engine more deeply and he said, look, who told you that the molecule is on the left side? Right? See, if you make a wrong guess, then you will not be able to extract work for that. Huh? So you need to, then he analyzed it in one way. He said, maybe I have to put some beam of light on both the sides, and then wherever I see the molecule. So then he said, all right, by putting this beam of light, I have to detect it. The detector will absorb that energy, so that will play the role of the sink. So he analyzed this in terms of physics, and he concluded that this engine will not work unless you still increase the entropy, not by putting the heat in some sink, but by trying to detect this molecule. Okay. So this opened up a very interesting idea, that the information of where this molecule is, my watch sometimes tends to run slow, so no, okay, it's working well so far. Yeah, and have another about 15-20 minutes? Yeah, sure. He said, therefore, instead of, so I am able to reduce the entropy here, right, by removing heat from the hot wall, but that entropy is going somewhere and it seems to be connected to the information which I am getting, right. So he gave a connection between information and entropy in the year 1930s or so, long before the current fad of information technology and so on, right. I will come back to this actually, because this is now almost the end of the 20th century. But I want to pursue this theme of information and it got pursued from an unexpected source. This gentleman was a well-trained engineer. His MSc thesis was on digital electronics, a lot of the things. He introduced the word bit for binary digit, and he worked for a telephone company, and he gave a definition of information which is very interesting. So you receive a message, like I tell you that Mr. Modi is the Prime Minister of India, have you gained any information by this? No, because you already knew that. So he said, you really gain information only if you receive a message which you did not know before. That means before you received the message, there was a collection of possible messages you could have received. In fact, my favorite example is this one. It happened to me, happened to many of us, that you are waiting in the hospital while your wife is in the labor room, and then the nurse comes out holding a bundle and she says it's a boy or it's a girl, right? So that's the simplest. So in Boltzmann's W would be 2, and this is what Shannon called 1 bit of information. Now maybe in the hospital there were actually 6 maternity wards where 6 husbands were waiting impatiently for the news. By the way, this is, I'm talking of 1980s, before ultrasound and all these tools told you, right? So now you can see there are 64 possibilities, 2 into 2 into 2 into 2 into 2. So W is 64. So Shannon said, look, it's inconvenient to multiply W. What would be sensible is information from this ward and this ward and this ward should be added. So let's take log of W, okay? Apparently he was not that familiar with statistical mechanics and so on, being a well-trained engineer, right? So this is his definition. H, it's called Shannon entropy, log of W, and why did he take the base 2? Because that will directly give you the number of bits. If you take log of 64, log to the base 2 is 6. 6 bits of information. Or another way of looking at it is I can encode the result of this experiment of 6 children being born by a string of 1s and 0s, each of which is a bit. So interestingly, he said information is the removal of your ignorance. When you were ignorant before you received the message, and then you gain information. So if you have a measure of ignorance, you have a measure of information. So you can see the parallel with what Boltzmann did. He said, I don't know what all the molecules are doing, but I know it is in one of some large number of states. Okay, so this is Shannon's definition of information. It's been used very well in statistics. I'm very tempted to go into this, but I will skip it. Okay, if someone is interested, I can tell you more. So on this theme of information, 2 gentlemen, now again not working in a university but in IBM, they took this idea further. Okay. So I already mentioned this, that if you record the position of the molecule in this heat engine invented by Szilard, you write down a 0 or you write down a 1 depending on the left or right. So let us say you go on doing this, alright. So you have reduced the entropy of the hot part of the engine, and where has the entropy gone? So the answer given by these gentlemen is, it's now there in the string of 1s and 0s. Now the strict rules of heat engines say you have to complete a cycle. After the cycle, the source may have lost some energy, the sink may have gained some energy, but the engine must remain absolutely the same. So either you have to think of the string of 1s and 0s as the sink, which carries some entropy, right, which is the Shannon entropy, because the molecule is moving randomly, so you don't know what the string is going to be to start with. Okay, but they actually took it one step further. Suppose I really want to finish the cycle, I have to erase this information. If you think about it, you think of computers as generating information, but they all erase information also, right? If the computer did not erase information, every time you do a calculation and all those results are stored, intermediate results, everything. Suppose you had a reversible computer which does not erase any information. As you go progress, the computer will get more and more full. It's like a person who doesn't forget anything, right? Ultimately the memory will get overloaded. So all computers sooner or later erase information. What is very interesting about what these gentlemen said is that this is not incidental, this is absolutely essential to the process of computation, the erasure part, and therefore there will be some entropy generated. One easy way to verify it is any of you can come and feel my computer, it's quite hot. Okay, so they focused on the step of erasure of information as a step which increases entropy. It's quite a fascinating idea, right? But I want to take it one step further. We all overuse information and communication technology. I am also guilty. I am using the computer, I am using this. I would like to think this is useful. Of course, people of the younger generation may say that looking at Facebook and so on is also very useful. But in some sense, number one, the computers generate heat. In fact, some of these trends, Google for example generates a huge amount of power. If Google moves to a small town in US, they have to double their power generation capacity. Okay, so we should also look at the process of computation as increasing entropy. Okay. So anyway, this is a controversial theme. Okay. So now this is 1970s, 1980s. Now you would think that by this time the basics of thermodynamics were well understood. So it was a bit of a surprise in 1990s, so almost into the 21st century. These two gentlemen started thinking about fluctuations in small systems, because by this time experimenters had developed tools to manipulate even a single molecule. So one of those tools received a Nobel Prize this year, as many of you may know, the optical tweezer. So you could take a DNA molecule, attach a small bead to it, and then hold it with this optical tweezer and stretch it, right? You could do experiments on these very small systems. Now these systems show a lot of fluctuations. So one principle of thermodynamics is that if I do work on an isolated system, the change in its energy will be equal to the work done. But suppose the system is not isolated. Suppose it's able to exchange heat with its surroundings, which are at temperature T. So this is what is called a bath. Okay. And most practical systems are in a bath, right? At some temperature, maybe room temperature. So then you can't say that just because I did some work on it, or I extracted some work on it, it may change the energy of the system, it may also change the energy of the bath. So for accountancy purposes, physicists starting with Helmholtz, Gibbs and so on, defined a new quantity called free energy. So the free energy allows for the energy absorbed from the surroundings. The actual formula is E minus Ts. So either you change E or you change the entropy, which means you have absorbed heat from the surroundings. Okay. Exact formula for free energy is not important. What's important right now is, for a thermodynamic system, the work done equals the change in free energy. But this is for a very small system. I mean for a very large system. For a small system, just by chance, by luck, it may be able to pick up energy just from the surroundings, right? And now the big change by 1990s was these could be measured. You could measure the fluctuations of this DNA molecule or any other small system, and every now and then you will find it heading in the opposite direction to what you would expect according to. So then what people said is, okay, so let's look at this formula. This is given by Dzerzhinsky. The most important part of the formula has not come out very well because of my black background. It's this bar, okay. Yeah, I hope you can all see a bar on top of this. So W is work done. See, if the bar had not been there, this formula would have told you something very obvious, that W is equal to delta F. Work done is equal to change in free energy. Now what Dzerzhinsky is telling you is, you repeat the experiment many times. Okay, you pull this DNA, every time you will get a different value of W, because the DNA molecule is in contact with a thermal bath. And when you pull it the second time, the random kicks which it gets from the bath will be different. So you will not get the same value of W every time. Nevertheless, you can still use it to calculate the change in free energy. Ultimately, what you want to publish in the journal is, here is the free energy of DNA as a function of the distance between the two ends of the DNA molecule. And of course, this is just one example. There are many other examples. Okay. So he gave this theorem, and this chemist, only 2 years later, physical chemist, gave an underlying principle which explains why this works. He said, for a macroscopic system, if it can go from A to B, it cannot go from B to A, because B has higher entropy than A. But for a small system, P A to B and P B to A are both there, but they have a certain ratio. If you remember my example, maybe I will even go back. What's now? Yeah, this one. So you notice that if I want to go from here to here, right, there's only one way of going, but if I want to go from here to here, there are 3 ways of going, right? So by keeping track of, so again, for a large system, this is trivial. It says this is 0, this is, yeah, if the system is in equilibrium, then these are equal and you have, this is essentially 0. But if the system is not in equilibrium, then you can actually look at the work done. So all these quantities actually keep changing. So this is now takes us almost to the current century, and these are very active fields of research. So these are called fluctuation theorems. So they tell you, so now our understanding of second law has greatly improved, because it's not a law in the same sense as Newton's laws. It's a law which, as I said, you can violate, but there are laws governing how much you can violate it. That also is there. Okay? Yeah, sure. Yeah. Yeah, the average is over W, and that's right. Yeah, it is the principle of detailed balance for macro states. Yeah. For microstates, the principle of detailed balance says P A to B is P B to A. For microstates. For macrostates, because the W for the two is different, you're right. So again, as I said, standing within 1 kilometer of IUCAA and NCRA, I have to say something about black holes, right? So black holes were believed to be the ultimate sink. You could throw anything into a black hole, and the black hole would absorb it. It would not give you anything back. Its mass would increase, and that was the understanding of black holes till 1970. Okay. In 1970, this person, Jacob Bekenstein, now in Israel, then in Princeton University, working with this person John Wheeler, who actually invented the term black hole. Okay. As I said, if he had patented the term, he would have made a lot of money. He also coined Wheeler is very famous for coining very nice statements which capture a lot of physics in a very short sentence. So he had a theorem which says a black hole has no hair. Now what it really means is, we don't see any properties of a black hole other than its mass, and if it is charge, and angular momentum. That's it. So it's kind of interesting, right? That you may have created the black hole by throwing in electrons or protons, or as he himself said, television sets, but it seems to forget everything about that, and right. So here is a classic example of information disappearing, right? So it's as if you could violate the second law of thermodynamics by simply taking all the entropy and pushing it into a black hole, and the rest of the world entropy would be coming down. Okay. Now Bekenstein realized, he was a young man, a research student at that time, that this was not actually so. He thought of some thought experiments in which you were trying to put energy into a black hole. Energy and mass, of course, we know are the same thing, and the energy has to be in the form of some particles. They have to have a de Broglie wavelength. If the wavelength is too large, it won't go into the black hole. And he concluded that actually the black hole has entropy, okay, and he gave a formula for it. Now this is the dimensionless entropy, so it's in units of Boltzmann's constant, and he gave a beautiful formula. It's just 1/4 the area of the black hole. Now Hawking had already said that as you go on throwing mass into a black hole, the area will go on increasing, and he even speculated this looks like the second law of thermodynamics, and Hawking himself and his co-authors, 3 authors, said this is only an analogy, there is no real entropy associated with the black hole. That's what they said in 1973. Then after Bekenstein wrote this paper, which was a kind of thought experiment paper, it's not a rigorous physics paper, then Hawking realized his mistake, and he wrote, of course, a Hawking paper which showed that black holes have entropy and they emit something like black body radiation, right? Now this is an absolutely huge amount of entropy, okay? I mean, this is much more than Avogadro's number or anything that you can think of for a black hole of 1 solar mass. But as I said, Hawking also said that the black hole will gradually, lose its mass by giving out some radiation. So it's like a hot body, and of course it gets hotter and hotter. The temperature of the black hole is inversely proportional to the mass, right? So now this left all theoretical physicists with a problem. I put all the entropy into the black hole, so the entropy is now there in the black hole. Now the black hole starts evaporating, and then it disappears. This is all just theory. The time taken for a black hole like this of solar mass to disappear is much more than the age of the universe. But as a thought experiment, you can imagine a small black hole will disappear. What happens to the entropy? What happens to the information? So I wish I could give you an answer, but the fact of the matter is, if you just go and Google information loss paradox, you will get maybe some large number of papers by a large number of string theorists, half of which will say there is information loss and half of them will say there is no information loss. I think people are gradually moving towards the idea that there is no information loss, which means that there is some kind of property of the black hole which we didn't understand earlier. But it's a very active field of research in physics. So I am almost at the end, but since I teach undergraduate thermal physics, I have taught it twice. So here are my suggestions. After all, this is a teaching institution as much as a research institution. I found that thermodynamics is actually difficult. I mean, you learn it and you think it's easy, and only when you lecture to the students and their faces look blank, and sometimes their answer sheets are also blank, then you realize that actually it's your fault. It's a difficult subject. Right? And the conceptual, the mathematics can be difficult, whereas kinetic theory, molecules colliding with walls and so on is a very nice subject, and it's mechanics, you can understand it. So you can do that first. Brownian motion, again, not that difficult. It's a random walk and you can easily demonstrate it. So to demonstrate it, I asked students to stand in front of our thing, toss a coin, move forward if it is heads, backward if it is tails, and the students gradually spread out. So they understood random walk and diffusion. Then you can use this to introduce entropy. I had a very nice experimental colleague. In fact, she is taking over the course from me. So instead of doing independent experiments, she coordinated the experiments with the theory part. And I think some of the things I told you about fluctuations, information, at least in PG level, they may convince students that this subject is not dead. Okay, you can make connections with biology. We are all heat engines in some sense. Okay, and even the whole of Earth is a heat engine where the sun is acting as a source, and the sink is, of course, the infrared radiation released by the Earth. Earth is about at 300 Kelvin, it radiates. And the biggest problem now is that if that radiation is trapped by carbon dioxide, then this heat engine may stop working. Okay. So let me leave you with this thought that thermodynamics is alive and well. There are still open problems in it, and maybe we can teach it in a way that makes it more interesting. Thank you. Yes, I see one there.
Sir, you talked about information theory.
Yes.
When you go for reversible gates, like AND or any one gate, so every time a bit of information is getting destroyed.
Irreversible gates.
Irreversible gates.
Yeah.
So that leads to the amount of heat generated, because delta Q is equal to minus KT log 2 for one bit of information.
I mean, that's the minimum.
Minimum. So lakhs of bits, lot of heat. So my question is it possible to construct irreversible gates at this juncture?
Construct without releasing heat, is it?
Yes.
According to our understanding of thermodynamics, no. And incidentally, existing computers release much more heat than the KT log 2 which he mentioned. And it's sort of interesting, if you, the reason why we make it much more than KT, that means we take the system well out of equilibrium, is precisely to avoid these fluctuations. See, in a physics experiment, I don't mind if some fraction of the molecules are doing something else, but if you are computing, you want all your computations to be absolutely correct. So you want the probability of, so basically I would say no. If you want reliable computation, then as far as I know, there are no array. Most computers actually release more heat than given by this fundamental limit.
I came across the literature that some like Friedkin or Toffoli gates are there which can be realized, but up till now I have not seen any implementation of those type of irreversible gates.
No, irreversible?
Irreversible without releasing any heat.
And I'd be interested in, if you're saying people proposed the gate but didn't give a physical realization.
Correct, sir.
Yeah, what has happened is very nice. There are some physicists who believe that information theory is a fundamental theory, and we should do all statistical mechanics and all that, teaching information theory first. But there is also an opposite view, which is I think that all your computers are really physical systems, which are carrying out some experiments. and you should apply statistical mechanics to these computers to understand how they behave. So it's interesting, both these views are there in the. So Wheeler himself toward the end of his life decided that information theory is the most fundamental thing. So in a characteristic Wheeler style, he coined a slogan, "It from bit." It means anything. The entire universe, if necessary, has to be constructed from bit. So if you follow Wheeler, it's it from bit. But incidentally, this person has visited ICER a couple of times. He's a computer scientist, but who has moved towards physics. He's in IIT Bombay right now, and he actually takes these gates and so on and analyzes them physically through Brownian motion, through other things. So it may be interesting to.
Thank you.
So, can I ask you a question? Let's take this time we have for understanding the connection between Bayes' theorem and the entropy loss. The slide which you have, can you allude to that for a 3 minutes short slide?
You're talking of the entropy of black holes?
No, the Bayes' theorem and.
Oh, the Bayes' theorem. Oh, the one, what I skipped.
Yes.
Okay. Yeah, I skipped it because it would take too much time, but let me go back. Basic. See, this is interesting because I'm taking you back one more century. So, you know, people like Carnot and Clausius are 19th century, and this is now 18th century. So, Bayes is his profession was a preacher, a reverend, but in those days, just because you were a preacher didn't mean that you didn't know calculus, probability and all that. But he didn't publish much in his lifetime. Now, there is a theorem which we all learn in probability. I have illustrated it with two kinds of fruit, pomegranate which is D and jackfruit which is H. You may wonder why these strange letters. That's because I show this in Bangalore, and the Kannada word for jackfruit begins with Ha, and that for this begins with D. Okay, so just think of it that way. So you can do fractions. 60% of the people eat jackfruit, right? 30% of them eat pomegranate. 15% of them eat both, right? Then you can ask, suppose I tell you that a person already is eating pomegranate, there is only this group, what's the probability that person eats jackfruit? That is the ratio of this to this. Whereas the other question, if I tell you that the person eats jackfruit and what fraction is pomegranate, it's the ratio of this. So these two are very different. These are called conditional probabilities. And this is the Bayes' theorem. Now, actually I chose these letters because Bayes he was not interested in whether people eat fruit or not. He was interested in how do people learn about the world. That's very fundamental, right? It's called epistemology, which is a term I learned only after joining Asimbrahim University. So H is hypothesis, D is data. Okay. Now, what we do is we have a set of hypotheses, and then when we get data, it cuts it down to a smaller number. Still may not get a unique one unless your experiment is perfect. You may still have a range of hypotheses. So that is what is called the Bayesian method. Now, information theory can be viewed as part of the Bayesian method. So Shannon makes a hypothesis that you have a set of messages, and he also postulates a probability distribution for them, which is called a prior distribution. Boltzmann also postulates a prior distribution. He says, before you made any measurements, all states of the system were equally probable. Of course, Boltzmann was very clever, or he had a lot of foresight in defining state as a region in a phase space which had velocity and position. Later on, this became obvious because quantum states obey this. Okay, so you always need this prior, and then you make measurements and you cut it down. So at least to some people, the Bayesian method, even though it's so old, includes statistical mechanics. It also includes information theory. So that's my. And actually, to all those who try to photograph, I assume you photograph the slides, not me. Then I'm happy to leave behind a copy of this presentation. Right? Actually, I have to say that when I was packing for this journey, I had this checked shirt and I had a striped shirt. I almost took the striped shirt, and then I put it. If I had brought the striped shirt, I would have been perfectly coordinated with my host, Professor Kumbar. But anyway.
Yeah. You said that in black holes the entropy is very high,
Yeah.
But black holes have very basic properties, and we tend to think that they have very low entropy. In terms, like they are the most, they don't carry any information as such. Right? Because
Well, the information is hidden, and as I said, this is not a closed subject. So if you think of a black hole classically, it doesn't answer this question. In fact, you can only compute entropy if you see. It's interesting that Boltzmann never actually calculated entropy. He calculated change in entropy because he didn't have Planck's constant in his hand. So he took the volume in phase space. Only when you divide by Planck's constant, then you get the number of states, right? So if you want to calculate black hole entropy, you have to do a quantum theory of black holes. That's the problem. Now, don't worry, people have done it. There are lots of people who have done it, and I can even give you a list of names who would make either in Bombay or in, Bangalore. But unfortunately, they are not able to model these astrophysical black holes. They model some other kind of black holes, which are easier to analyze. I won't say easy in string theory. So there, they are able to actually compute the number of states and confirm this area theorem. So at a purely theoretical level, no one has made these black holes. No one has added heat to them. I mean, it's not possible. But so the belief that black holes have this huge entropy. So by the way, one thing I passed over very quickly, I said area, but entropy was dimensionless, S. Area was dimensional. So let me, this is the unit. The unit contains Planck's constant. It should, any formula for entropy should contain Planck's constant for the absolute value of entropy. For the change in entropy, sometimes it will cancel. So that's the point. This thing is 10 to the minus, this LP, Planck length, is 10 to the minus 33 centimeters. And the size of the black hole is kilometers. So you can imagine if you measure the area in those units, you are going to end up with a very large number.
so, is it like each Planck volume of the black hole contains one bit of information? Is it
something like that? Planck area.
Each Planck area. Okay.
I think the theory is given. String theory is not the only theory for black hole entropy. Abhay Ashtekar, who again visits Pune very often, has his own models of quantum black holes, and they are also able to compute entropy. But as I said, this is a subject which I treat with a little respect and distance because it is really the highest frontier of theoretical physics right now. I'm much happier with entropy in condensed matter, or
See, in that experiment of a molecule getting on the hot wall and the piston moving on the left, when you move the piston to the left before the molecule actually gives away the energy, so something is done outside that system to move the piston.
No, it's true, but because there is no molecule bouncing against the piston, you're right. That's the external agent which is taking useful work out of the heat engine, right? So I could imagine a wheel and some weight or something, so the weight moves up and down, something like that.
True. No, what I was thinking,
it's an external agent, yes.
Normally when we consider the entropy, it is in that totality, that what is even in the external world, whether the entropy is increasing overall or not. This isn't it, this becomes a kind of isolated system.
Okay. So in the case of heat engines, when we talk of entropy at the source and sink, we never talk of entropy associated with the work done, because the work done goes into, say, for example, your motorcycle moving, and that is considered to be a zero entropy system. So you're right. I mean, a system which is doing work is not isolated, but the work part, not the heat part, is not carrying any entropy. That's my understanding.
One more question about that Crookes formula.
Identical states.
Identical particles. I mean,
particles.
Yeah.
No, A and B are supposed to be two states of the system, no?
Yeah. Okay.
So we are not talking about particles. No, the place where I smuggled in identical particles or non-identical particles is this. Right? So if the particles were identical, then these four states would become only one state, right? And these would become one. So actually, this tells you something interesting. If these particles were bosons at some low temperature, then your fluctuations away from equilibrium would actually increase. Because see, right now the fluctuations are small because you have 6 states here and only 1 here. But suppose all these become a single state with you know, 2 L's and 2 R's, and since they are identical, you don't know which is L and which is R, right? So it's true that both systems show enhanced fluctuations. So, but this was meant for systems of distinguishable particles.
Questions? If no more questions, okay. Yeah, I would like to inform you, sir, that this presentation has been webcasted. So it is also available on the website, and several students from colleges are also able to view this directly.
Fantastic.
Yeah. And secondly, some of the students must be wondering why a small piece of paper, A4 size paper, was given to you. We want you to write a short summary, a technical summary of this lecture, and we will evaluate it, and the best couple of them would get a prize, mostly in the next year, when we start our next semester colloquia. Sir, you would like to?
Well, we really had a very lucid lecture here by Professor Rajaram. I knew him since he joined here NCRA as a director, and at that time I was heading the school in the electronics department, and he came there and we had discussions on various things. He gave talks on the optics, the Gaussian distribution, the Gaussian shape of the beam and how it disperses and so on. A very interesting topic there, and in fact I thought that perhaps he would like to talk something on that some other time, and that was very informative, and we enjoyed it a lot. Today we do see that starting from the very simple concepts, absolutely at a ground level, he raised the whole thing very slowly but definitely and steadily to the black holes. So that beauty he has, the way he is a great teacher, and as you can see how lucky those students are in that university, which is the university, I mean I just forget the name, but we need these kind of people, and I'm sure you must have also enjoyed this lecture quite a bit. It has given, it gives certain food for your thoughts. You will now at least start thinking about what this entropy and wherever, in what so many different ways it is going to appear, the reversibility, irreversibility. In fact, very interestingly, that answer which he has given, I was looking around for that. Those fluctuations, answers in the fluctuations, that it is really, don't have to worry about the basic equations which are reversible, but this irreversibility is just the counting of states from going from one end to the other end, and that's about it. So that was very interesting. I certainly learned these things, and everybody here must have learned something or other, and you will certainly get lot of things to think about. With these few words, I think let us thank Professor Rajaram. Thank you, sir. And
no? Oh. No, I have just a suggestion to. Okay.
That is the reason why I announced it at the end, not at the beginning, so that now they will have put their own minds together rather than looking at something and writing things. Okay, so I
submitted, then I will
sure
send it to you.
Thank you. Yeah, so let's thank Professor Rajaram Nityananda for taking time off and coming here and giving a very nice talk on thermodynamics, and a hot topic over several centuries. And I would also like to thank the Department of Physics, the faculty at the Department of Physics and the non-teaching staff for making this possible, and also the students who have come here, students and faculty who have come here, even being Diwali vacation starts, so it's great to see also many of you here. And I would also like to thank Grey Eye Vision and the e-content studio of our university, Dr. Sarang Joshi and Mr. Hardikar, for making this webcasting possible. And I take this opportunity to wish you all a very happy Diwali, and hope you enjoy and come back and start working in a more serious note on, and hope the entropy increases as we go to the end of this year. Thank you very much. Please submit the one-page summary to me by 5 o'clock today, right? Latest by 5 o'clock today. Those who are interested, please submit them to me in chemistry department. Or you can collect them together and bring it to me. That's also fine. Thank you very much.